Hi guys, my name is Mac Durham. I'm going to go through today and tell you a little bit about how LabView works, how you can connect it to your myDAQ to collect data, and how you can analyze this data using some of the built-in functionality within LabView. So the first thing to do is to go and download this script called FFT of myDAQ.vi. So VI are files which can be opened by LabView. There's the directions in your lab script that tells you where you can download this from on Blackboard. So the first thing you do after you get it downloaded and open it up in LabView is to go to Window and Show Block Diagram. That's opened up on my other screen, but I'll move it onto this screen here so you can see it. And the block diagram basically shows you what's happening under the hood within this LabView script. So the first thing I like to do is go to Window again and tile left to right. This puts your front panel on the left-hand side and the block diagram on the right. Now, many of you probably have used LabView and only looked at the front panel. If you're not writing the script, you don't need to know anything that's in the block diagram. So the inputs, the front panel shows things like inputs and outputs. Here you have two inputs and you have two graphical outputs. And you can see what calculations you're doing by looking at this block diagram here. So we're inputting the sample rate and the sample time. You can see where various things correspond to each other by double-clicking these icons in the block diagram, and it'll basically highlight where they're at on the front panel. So you can see how they interconnect to one another. Now, what we're going to be using this VI, which we've written for you already, and you downloaded from Blackboard for today, is basically to analyze the output of your oscillating circuit. Now, to do this, we're going to have to specify a sample rate. This is going to be how many samples your myDAQ is making per second. And it's given in hertz, and we have a sample time. So currently, we're going to, by default, this is going to take 2,000 samples per second for 3 seconds, which yields 6,000 samples. Now you can run this script by pushing this arrow, which I just pushed a second ago, on both on either the front panel or the block diagram. Both will do exactly the same thing. If for some reason your code breaks and you can't get it stopped, you can push this stop sign, which will quit it from executing and allow you to regain access to changing various parameters in your code. Now, we'll go through a bit about how this myDAQ assistant works, this DAQ assistant here. But first, we'll talk a little bit about how LabView operates. So this code has two controls that I specified by before, the sample time and sample rate. We can multiply those together and we get the number of samples, which it outputs. Now you can see that these are not connected. These are connected by these small wires here. So LabView is a graphical programming language, unlike Python, which is a text-based programming language. In LabView, you connect these various functions together with these wires. And the type of wire here denotes what kind of data it contains. So here we have an orange wire, which means it's a double precision number, whereas the data coming out of your myDAQ assistant, which is the data which is collected from your myDAQ, has this dashed blue line, which is called a dynamic data type in LabView speak. And this contains both timing and amplitude information. So here you're plotting the data that's being output by your DAQ assistant, and this wire contains both the information along the x-axis here, which is the time, as well as the amplitude here, which is the voltage that's being measured by your myDAQ. So we have negative 2.3 volts or so here at the peak output. Now, the data from this DAQ assistant we're plotting directly in the time domain, and then we'll run it through a VI called spectral measurements, which is basically takes something called the Fast Fourier Transform of this signal. Now, the Fast Fourier Transform was developed in the last 50 years or so, right at the advent of modern computing. And this thing that's special about the Fast Fourier Transform is it's fast. So the classical discrete Fourier transform on a computer runs in n squared time. That's computational time. So n is the number of samples in your signal. And however, the fast Fourier transform runs in n log n time, which can make it quite a bit faster, especially as the number of samples increases. So in all VIs, the inputs are on the left-hand side of this VI. So this is a VI within a VI. Like Python, you can nest programs inside of one another. And the output's always on the right-hand side. So we're plotting the output here. We're plotting the amplitude of the fast Fourier transform. We're not plotting the phase information. You can plot it, though, if you're interested and see what it looks like. So we can double click on the output of that fast Fourier transform. You can see this highlights this panel on our front panel window. Now this is the raw output of our fast Fourier transform. You're probably familiar with something called the Nyquist criterion, which means that it's a simple way of saying that you cannot resolve a frequency within your signal that's more than half your sampling rate. So right now we have a sample rate of 2,000 hertz, which means that we can only resolve frequencies in that signal which have a maximum of 1,000 hertz. Now if we take and reduce the sampling rate down, let's say 1,000 hertz, it means that the maximum or the highest frequency signal which we can resolve is only going to be 500 hertz. You can see now that's changed this to 500. So we can zoom in our signal that's being produced by my oscillating circuit. So we're going to zoom in the first second of signal, and we can see this square wave quite clearly. Now to estimate the dominant frequency in the square wave, we can count the number of troughs here. If you count them, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pulses in 1 second, so around 13 hertz. Now we can zoom in on this signal, as I just did in this other graph here, just by changing this first or last number and the labels on this plot. So we can just simply type in, let's say 50 here, and we'll zoom in on the first part of that signal. And indeed, we have a peak here of at around 13 hertz. This might not be exactly 13 because we have this part at the beginning and the end, and that's going to be an extra pulse which is squeezed into that signal. We can more accurately measure the height of this, or the location of this peak by clicking on this cursor symbol here. This is this crosshair symbol. You click on that, then it'll allow you to move these vertical yellow lines, and you can put that right on top of that peak there, and see we indeed get about 13.6 hertz out of this. We can also move this one here and measure the secondary peak that's around 40.5 hertz. And that'll allow you to basically measure the dominant frequency within any signal you generate. So the next thing we want to do is filter this signal. Now, as you've probably gone through in your lecture class, you know what the Fourier transform of a square wave is. It has frequencies that are contains frequencies that are much higher than that of the dominant frequency of this square wave. You can see we have these higher frequency components here. This peak, these multiple peaks here. You can measure and see what the location of each one of these peaks is, for example. So one thing we're going to go over in this tutorial is how to filter this signal. Now this filtering, we're going to use it to basically recover a sine wave from the square wave, but you can also use it to remove certain frequency components in your signal. So let's suppose that we had a sound signal rather than a signal from our oscillating circuit, and we wanted to isolate the sound from a particular instrument. For example, if we wanted to isolate the sound from a bass guitar, we'd be more interested in what's happening here at lower frequencies, and we would want to filter out the higher frequency noise. To do that, we use something called a low-pass filter. It'll pass all the frequencies below a certain threshold and eliminate all the ones above that threshold. Just to give you an idea of how this works, we're gonna implement one on our block diagram here. So you can put additional VI onto your block diagram by right-clicking anywhere in your block diagram, and this opens up this thing called a palette. And you can see there's lots of different bits of code here. You can drop onto your block diagram to allow you to build more complex pieces of code more easily. The one we're going to be interested in today is a filter VI, which is located in this Express tab. See if you navigate to Express. You can go to Signal Analysis and then to Filter. Now if you click on this, you can take and drag this onto your block diagram. You cannot put this on your front panel. You can only put it on your block diagram. So we'll just go ahead and accept it's on low pass filter with a cutoff frequency of 100 Hertz. We'll just make a note of that. We'll go ahead and hit OK here. So what we're interested in doing is showing the signal before and after filtering. So we already have all the tools we need to plot the output of this filter. They're right above here. So we're going to simply cut and paste these graphs here and the spectral measurements VI and paste it after this filter here. So what we want to do is just draw a square around all the bits you want to cut and paste. So you just do that by clicking and drawing a box around everything you want to cut and paste. So we'll draw a box right there, and we'll simply hit Control-C to copy it, and then Control-V to paste it. Now you notice this is going to be all highlighted. You can drag this down here, and we can wire this up to the output of our filter. So we simply go to this output of this filter, connect that to the wires here that lead to these additional plots, and then we're going to connect this input of this filter to anywhere in the output of our DAQ assistant. So the signal is the same everywhere from this point here, where the data comes out of the DAQ assistant, to where it goes into the spectral measurements. You can connect this wire anywhere you want to between those 2 points. So you can notice on our front panel, these new graphs that appeared on our front panel, they kind of appear in any old place. So we need to move these down and put them in a place which is more sensible. So we'll put this filtered signal underneath the raw signal here, and we'll locate this Fourier transform of that filtered signal and put it below, in a similar position below our unfiltered signal. Now you can comment anywhere on this block diagram by simply double clicking here, and you can just, like in Python, you can comment and say what you're doing in different parts of that code. So this is going to be, currently have a high pass filter. You can change that however you like, but on the front panel we can just label this is our unfiltered signal. We can use double click, and we can label this below, these 2 graphs below, as our filtered signal. Just so we can keep track of what is what. So if we run this, it'll collect a bit more data, and we can open up this filter and see what we've done to the signal. So again, we have a low pass filter. We have basically cut off everything that's above 100 Hertz. And if we zoom in on this data here, this is our unfiltered signal. This is our filtered one. We can see that we no longer have a square wave. We have this little peak on this side of it. And more importantly, you see in this Fourier transform that we basically eliminated everything that's above 100 or so Hertz. Now we have some things leaking out through this filter that are slightly above 100 Hertz. It's not going to be, this filter doesn't cut off everything above 100 Hertz, but it puts the threshold right at 100 Hertz. So some things will be leaking through. It's important to keep that in mind. If we double click on this filter here, we can see, we can change the type of filter which we're using here. So filters are quite useful for both isolating, for example, certain instruments within a more complex piece of music where it contains many instruments which might be divided or might be separated in the frequency which the various instrument produces. But it also can be quite useful for removing noise. For example, if someone has a crackly microphone, you can remove that high frequency noise. You can also remove noise, let's say, from the mains. So if you plug something into the outlet, there's going to be normally a hum at 50 hertz, which is the frequency which the DC electricity oscillates at. So you can remove those forms of noise as well. So we know we have a dominant frequency in our signal of around 13 hertz. So let's cut off everything that's above 13 hertz here. So we can run this in many different ways. You can basically use a band pass filter to isolate a particular frequency you're interested in. In this case, we're just going to get rid of everything that's higher frequency than 13 hertz. We'll not make this exactly 13. We'll make it a little bit higher. So we won't. If we make that right at 13, it'll kill our signal at 13 hertz quite a bit. So we'll make it a little bit above 13. We have different types of filters we can use. These are all digital signal filters. You can have a play around with this, and if you're interested, you can look and see what each different types of filter does. But we're not going to concern ourselves with that in this tutorial. If you hit OK on here, we can run this again, and we can look at the output. So you can quite clearly see that we have a much more sinusoidal function than we did before. So before we were getting rid of everything above 100 hertz. Now we're getting rid of everything above 20 hertz. And we can see in this Fourier transform that we have basically eliminated our signal above that threshold. Okay, so the last thing I want to go over is how to change, or a couple more things I want to go over, is how to change the input on your myDAQ assistant. So some of you are going to be doing an experiment on analyzing various audio signals. And to do this, you're going to instead of using the analog input 0 on your myDAQ assistant, or on your myDAQ, you're going to use the microphone jack on it. And if you want to use the microphone jack as opposed to that analog input, you need to go to this DAQ assistant before you start collecting data and change the channel which you're measuring. So if you double click on that DAQ assistant, it'll open up this window here. You're going to right click on voltage and go to change physical channel. Now you can go to you can change between analog input 0, analog input 1. You have audio input left, audio input right. If you have a stereo microphone, you can collect data on either microphone, on either left or right input. If you have a mono microphone, then you only have signal coming in through either the left or the right. So if you're not getting any signal initially, you might want to change that over to the opposite one. So we'll put this on the left, and this will set it up to basically collect data from our microphone instead. Okay, the last thing I want to go over is how to export data from these graphs. You can plot these graphs directly with a screenshot, but it's a lot better to actually output the data from this graph and collect it so you can analyze it with another type of program. So to do that, you want to right click in this graph here, and you can from that you can just simply go to export and copy this data to clipboard. So you can copy it to clipboard and you can paste it in any program you like. You can also export the data to Excel and save it, for example, as a CSV file, which you could read in with Excel or another software like Python. That's it, guys. Let us know if you have any questions. Thanks.